of the main effects that most of which were already known to you. I forgot to make an important point about length contraction, something that you already know about. I wanted to make sure that you remember is that length contraction just concerns the dimension along the direction of motion, okay? So what is perpendicular to the direction of motion is unaffected. So length contraction just concerns that specific direction. So, we stopped here last time, particularly at the previous slide, when I was talking about relativistic aberration, so the relativistic beaming, essentially. Another aspect which is affected by relativistic motion is the solid angle. So, for example, let's suppose that you consider some radiation emitted by the source. So, if you look at the upper panel, here you are interested just in the radiation emitted within this solid angle, delta omega prime. Okay. So you wonder, and this is at an angle theta prime with respect to the line to the direction of motion. So this is the co-moving reference frame. So you wonder, okay, you already know the corresponding theta angle, and this is the reminder of the formula connecting the two angles. So the aberration, we already know that. And in particular, we already know why in this figure theta is smaller than, and in particular, the cone is closer to the direction of motion of the source. Now we want to investigate how the solid angle itself changes. So calling delta omega prime the solid angle subtended in the solid angle in which a bunch of rays are emitted, you wonder. So we set ourselves the task of calculating delta omega. So the corresponding solid angle in the observer lap or fixed frame, whatever you want to call it. How can you do that? Well, just so let's calculate. Let's express d omega prime as a function of both the polar angle theta prime and the azimuthal angle phi prime. And well, sine theta prime is just minus, it's just the derivative of minus cos theta prime. So if you also notice that the azimuthal angle, so the angle which spans the direction onto the plane which is perpendicular onto this plane, essentially. So this is the direction of the polar direction, and the azimuthal direction is here. So phi describes the position on a plane which is perpendicular to the line of motion. So is unaffected for the very reason I just told you at the beginning of this class. So essentially, an interval, a small interval in phi, d phi, is equal to d phi prime. And then it's just a matter of calculating, of deriving. So if you take the formula of cos theta prime that I put here above, and you just work out the derivative. So you derive with respect to theta, this is a function of theta, I explicitly wrote here the result, and I always invite you to check yourself the calculations that I put on the slides. So this is just a matter of derivative of deriving this formula here. So if you work out, if you pay attention, I'm not going to comment on every single calculation here. This is just first undergraduate course stuff, or calculus 1. So you see that there's some some terms that vanish. So you're left with this. And if you replace this into the major formula of d omega prime, you see that this guy, so d cos theta prime, is just this guy here. And if you pay attention, you remember the definition, how we defined the Doppler factor, delta, yesterday. This is indeed delta squared. The denominator should be familiar, and then you have 1 over gamma. But 1 over gamma squared, I'm talking about delta squared, is just, I remind you that gamma is 1 over square root of 1 minus beta squared. So 1 minus beta squared is 1 over gamma squared, just like that. So overall, all this part that I highlighted is just the Doppler factor squared. So this is delta squared sine theta d theta d phi, which is d omega. So delta squared d omega. So the relation connecting the same solid angle as evaluated, as calculated in the two reference frames is reasonably simple. And again, you see that delta to the prime there's just a factor of Doppler factor squared in between. And if you invert, in particular, if you assume you know the solid angle in the comoving frame, so d omega prime, and you want to calculate the corresponding solid angle in the fixed frame, this is suppressed. Let's assume that for that specific direction, the Doppler factor is greater than 1, so there is a boost. Remember that it depends on if you are for reasonably small, not too large values for theta prime, the Doppler factor is greater than 1, so you have a boosting, not a boosting. Okay, so for example, like in this case, surely in this case, if you look at the upper panel, so theta prime in the comoving source, the angle is smaller than 90 degrees. So for sure, the Doppler factor is greater than 1. So indeed, there is a boosting. And indeed, theta is smaller. It's closer to the line of motion. Remember the relativistic beaming? And the corresponding effect on the solid angle is that the solid angle decreases by a factor of Doppler factor squared. So it's smaller. And that's what is also shown here in the figure. And that should make sense if you think, well, if you think of the figures that I already showed in the previous class, in which half of the sky is compressed, kind of compressed, when the motion is relativistic and particularly ultra-relativistic, is just compressed down to a narrow cone. So it means that a relatively large solid angle gets much smaller. How much? Delta squared. Okay, so this is also worth remembering. And so as you can imagine, Doppler factor, the Doppler effect in astronomy is really important and is ubiquitous, I would say, since we are talking about sources of radiation which can be moving with respect to the observer, so this is just standard. On several different scales, you can think of stars belonging to our own galaxy which are moving, as every object in the galaxy is moving, also ourselves with the sun. So there is a relative motion. So if you're looking at a star, at a given star, there is the Doppler effect comes into play. There's no way you can escape it. So this is worth spending a few words about conventions. Typically, in astronomy, so through the Doppler effect, you can measure the projection of the velocity onto the line of sight, of course, because that's what is what comes into play into the Doppler factor itself. And in particular, so if I call beta r the radial component of the velocity, by radial I mean the projection of the velocity onto the line of sight. Okay, so radial in this sense. Do not be fooled by maybe sometimes you might have to deal with a star. So radial doesn't have anything to do with the radius of the star. No, it's radial in the sense that you think you are the center of a sphere, and radial in that sense. You're looking at the source, so radial is just projection on the line of sight, okay, to the source. And the convention is that whenever the source, for example, a galaxy, is receding, so the projection of the velocity onto the line of sight, if you take as positive direction the one which is going outward, so in that case, you call this velocity or the radial projection of the velocity as positive. So positive is when it is receding from you, okay? And in this case, you have a red shift because the radiation is shifted towards longer wavelength. So if you think of the visible spectrum towards red, so red shift. There is a shift in the wavelength of the photon towards red. So the wavelength increases or the frequency decreases when the source is receding. And so in this case, we note as VR, so the radial projection of velocity, positive. In the opposite case, as you have, for example, a star within our own galaxy, which is a projected component of velocity towards us, so it's approaching. Okay, in that case, the convention on the sign is as a consequence is negative. But if you pay attention to, well, I can recall it, but to the definition of the Doppler factor, there was a cos theta, where theta was the angle between the direction of motion of the source and the line of sight towards the observer. So if you pay attention, comparing here how I defined beta r, and in that case, beta cos theta, there's a minus sign difference. Because in that case, when the projection of the velocity to you is approaching is going towards the observer, in that case, we use theta, so plus the plus sign. In this case, this corresponds to the minus. So it's not just to make things messier. It's just a matter of, in astronomy, this was the convention. So when you want to apply the Doppler factor formula that we learned, you have to pay attention to that. So in particular here, when I want to calculate the frequency shift of a photon, as where nu zero is the frequency of the photon emitted in the comoving source frame, and nu is the measured frequency. So nu over nu zero is the Doppler factor by definition. So this is just delta minus 1. Delta is this guy. So that's what I was mentioning. So you see, in that case, so for the convention we adopted for the figure we used to define cos theta when we introduce the Doppler factor, and in this case, you have to make sure that you're not losing the minus sign here. So when you replace this in here, minus beta cos theta becomes beta radial. Okay. And if you don't remember, just think of one case. Think of the source which is either receding from you or approaching, and you consider from this point of view, from the sign of beta r, and in the context of the figure defining the Doppler factor, what you are expected to, what is the value for theta. It's a kind of, if you want, to put it in another way, it's kind of replacing theta with pi minus theta. So that's why the cosine changes sign, just like that. So it's just a matter of, and it's interesting to consider, particularly when the motion of the source is not relativistic. So not relativistic means gamma essentially is 1, Lorentz factor 1, and beta is much smaller than 1. And if you expand the first term, So gamma is 1. So 1 over 1 plus something small is 1 minus something small. Okay? Taylor expansion. So 1 minus beta r minus 1 minus beta r. Let's have a look whether it makes sense from the point of view, at least from the qualitative point of view. Well, this is a frequency shift. So when the frequency increases, it means that somehow the source is approaching. So when delta nu is positive, the source is supposed to be to be approaching. And indeed, if delta nu, this guy here, has to be positive, it means that beta r has to be negative. And indeed, beta r or VR, which is the same, negative indeed means that the source is approaching. So, okay, the sign looks okay. So, summarizing, delta nu over nu zero in the non-relativistic regime, so with the source, and there's plenty of examples, also in astrophysics. Also, if you take all the stars in our own galaxy, typical velocities are orders of magnitude. For example, or I don't know, the velocity of the Earth around, the orbital velocity of the Earth around the Sun is just 30 kilometers per second. So your orders of, in this case, 10 to minus 4, the speed of light. So all these cases you can easily apply the non-relativistic limit. So this formula here. If for some reason you are working on wavelengths rather than frequencies, well, the corresponding shift in wavelength is this way, is this one. There's just the beta r is positive when the wavelength when there's an increasing wavelength. So when there is a redshift, when the frequency perceived by the observer, measured by the observer, is greater, is longer than the co-moving frame wavelength, and in that case, indeed, it's because the source is receding from us. So also, you measure what you measure on a practical basis. What you measure is either delta lambda or delta nu, and from that you can infer beta r. So it's the Doppler effect in astrophysics is a really powerful tool to measure at least the radial component of the velocity of something. Of course, it's a relative velocity with respect to the Earth. So when you want to calculate, for example, the relative velocity with respect to the barycenter of the solar system, then you have to compose velocities as you know. In case you wonder why delta lambda over lambda 0 is plus beta r, well, I set this as an exercise for you. Just make sure you can prove. So starting from here, delta nu over nu 0 minus beta r, make sure you can derive this. You can consider delta lambda as something very small. So delta lambda over lambda 0 is indeed, we are in the non-relativistic regime, so these quantities are much smaller than 1, okay? So you can treat as they were infinitesimal quantities. So instead of delta ni, you can consider d ni and delta lambda d lambda. Simple exercise for you to test your. And if you have troubles, then you let me know. As I said, the red shift. So the shift towards red is defined with the letter Z. This is universal notation. And Z, by definition, is just delta lambda over lambda 0. Okay? So a positive redshift means that the source is receding from you. And in the non-relativistic regime, so from what we saw in the previous slide, delta lambda over lambda 0 is just beta r. So in the non-relativistic regime, the redshift is just, and the redshift is typically what you measure from the radiation. How practically? Well, practically, there are some emission in this plot, some absorption lines. So you take the electromagnetic spectrum of a source, and you see some absorption lines. which correspond to some specific atomic lines. So depending on whether they shift along the spectrum, so in the above case, for example, when the source of radiation I'm considering here is this is a binary star, so I'm looking at the spectrum of the star B. So you see, when the star B is here, we are looking at the system from this point of view. In this case, when it is here, it's approaching us. So in that case, we expect a blue shift. And indeed, the absorption line, you see, they're shifted towards the blue part of the spectrum. So frequency has increased. While in the opposite case, of course, you see the opposite effect. When it is here, it's receding from us, so there is a red shift. So you measure the red shift, the shift in wavelength, you derive the radial velocity. Radial, do not, as I want to stress, because in the past there were a few students who got confused about that. Radial has nothing to do with the radius of this orbit. Radial in the sense of projected along the line of sight, okay? That's important. So you see, this is just one of the examples in which you can derive a physical interesting quantity like a velocity, like the speed of an object, just measuring spectrum, measuring a red or blue shift. But the redshift is also very important in cosmology, or whenever you want to express, measure distances of objects out in the universe. And this is called cosmological redshift. And this is here there's an important point to make, because some people think that, well, all of you know that the universe is expanding, and this expansion can be described by the Hubble's law. So the recession velocity with which all the galaxies are receding from us is proportional to the distance. So you know, if you manage to measure the velocity with the Hubble's law, you can kind of measure the distance. Okay, simple in principle. But this is not a Doppler effect. This is quite, I don't know how subtle it is, but sometimes this is going to be confusing. You say, okay, but the source is receding from us. So I've got a source of electromagnetic waves which is receding from us. So the red shift is due to Doppler effect. No. In this case, the thing is, and that's why it is called this cosmological redshift. The reason for this shift is because the space itself is expanding. It's not like the Doppler effect. In the Doppler effect, the space is always the same. It's just the source is getting further and further, or is approaching us. Or either the source or the observer. We know that talking about electromagnetic radiation, it's a matter of relative motion. In this case, it's the space-time fabric itself which is expanding. So to mean that, here, let's suppose that, and there's a parameter in cosmology which describes this expansion, which is the so-called scale parameter, which gives you the scale of the universe at some point. So let's suppose that it is usually denoted with the letter A. So let's suppose that at some point a galaxy emits a photon, and this photon has a wavelength lambda 0, and the scale parameter of the universe at that very moment, so at the emission time, is AE. We call it AE. So AE is nothing but the scale parameter of the universe at the emission time of this photon. So now, while the photon is traveling to reach us finally, the universe goes on expanding. So the space-time itself expands. It's stretching. It's all the space-time in between. So all the space-time between our own galaxy and the galaxy which emitted the photon is all the space-time is a stretching. So you have a wave traveling along a space-time which is all stretching. So the result is that the wavelength increases. And if we call lambda the final wavelength, that is the wavelength of the photon at the time of observation, at that time the scale parameter will be different. And so we call AO to mean the scale parameter of the universe at the observation time. And because of the expansion of the universe, the two scale parameters are different. And in particular, their ratio is exactly the ratio of the two wavelengths. So the red shift that we observe, indeed, is a measure of the distance, because this ratio, lambda over lambda 0, is nothing but the ratio of the two scale parameters. And indeed, you can call it this 1 plus z. And this is the cosmological redshift. Okay? And so this is related to the distance because of the Hubble's law. The further the galaxy which emitted the photon, so the larger will be finally the ratio between the two scale parameters. As correspondingly, the larger will be the red shift, and so z. So this is a subtle point, but it's important. It's important. It's worth stressing. So you see, what happens here is something different. It's not just that the source is moving, either the source or the observer is moving. It's the space-time itself in between. The space-time in which the wave is traveling, which is stretching, continually stretches. So it's different. It's a little bit different. Okay. So this was it for the redshift. Let's switch a little bit topic. Let's consider the so-called distribution function, what it is. Okay, let's assume that there are some particles moving in space. A group of particles with very similar velocities. You have a bunch of particles in the region of a space, and they have almost the same momentum, okay, linear momentum. So you can consider the corresponding volume element, where the volume is meant to be in the phase space. So you have 6D space, which you have the 3 spatial and the 3 momentum components, okay? So if you consider the comoving frame, or better, the comoving phase space frame, well, in the comoving frame, all the particles are essentially at rest. Not all of them, because since not all of them have exactly the same velocity, they cannot be all at rest in the very same frame. But nearly, since their momentum are nearly the same, there is a comoving system in which they are almost stationary. Okay? Essentially, they don't move, or they move very little in this frame because of the definition of comoving frame. So in this volume, you can define dV prime as the elementary volume in the phase space, in the comoving phase space. Prime, I remind you, prime stands for comoving frame. So in which there will be, of course, a spread in the 3 spatial coordinates as well as the 3 spatial momentum components. Now, what we want to do now is to figure out, to calculate, to move back from the comoving frame back to the fixed or observer frame, and that volume will have a corresponding value, which we call dV. So we want to investigate what kind of relation, what's the relation between the volume in the comoving frame and the volume in the lap frame. Again, so we have to transform all these infinitesimal elements from prime system to unprimed system. Again, the rule is go through Lorentz transformations. So let's have a look how it works. Again, for the sake of clarity, I constantly assume a boost along x, okay, just to make things easier. So y and z components are unaffected. So are their differential quantities. So dy and dz just do not change, just like that. If you have in mind, if you remember Lorentz transformation, of course, the direction along the motion is easily affected and is affected by a factor of gamma. Here we are moving from the co-moving frame back to the fixed frame. So there's the contraction, Lorentz contraction. So the dx prime, which is the length of this kind of 6D box, is shortened, is contracted by a factor of gamma, okay? Lorentz contraction, just like that. What happens on the momentum? Well, again, the y and z components are unaffected for the very same reason. Remember that the momentum energy vector, is something which indeed, again, transforms according to Lorentz transformation. So again, we have to use Lorentz transformation for the momentum energy as well. And in particular, the only component that is affected is, again, the component of the momentum parallel to the direction of motion. Again, just use Lorentz transformation, and you see that this is the factor coming into play. So again, the momentum increases by a factor of gamma, plus this term. But the second term here, beta dE prime over C, is actually negligible with respect to this one. Why this? Well, dE prime is the energy interval in the co-moving frame. But in the co-moving frame, all the particles are nearly at rest. They are nearly at rest because that's the co-moving frame. So it means that the difference in energy is just the kinetic energy in the non-relativistic regime. They are nearly at rest. So to estimate dE prime, you can also take the non-relativistic formula as a function of P, for example. P squared over 2m. That's the kinetic energy in Newtonian physics, expressed in terms of as a function of the momentum rather than velocity. P squared over 2m. And if you work out the differential, this is just P over m dP. But you see, and this is this guy here, but P, again, we are in the co-moving frame, so P is of the order of dP itself. They are nearly at rest. So given that dP is telling me the spread of the momentum, but the average momentum here is 0. So it means that the spread in P is just delta P, is of the order of delta P. So this is all to say that this dE prime is dP prime squared. So it's a second order infinitesimal quantity. So it means that if you infinitesimal, it means that you are infinitely small. So it means that this guy is negligible with respect to this. This is dP prime. Okay, let's forget about x. dP prime. This is dP prime squared. So if you've got something small, squared is negligible with respect to. Okay. So it means that, as a matter of fact, this term can be neglected at all. So putting everything together, you say this very simple property. So that the gamma coming into play due to the x coordinate cancels out with the gamma due to the corresponding momentum. So the net result is that this volume, this phase space volume, is invariant. Invariant with respect to what? To Lorentz transformation. So we found, finally, that this elementary volume in the phase space doesn't change whether you calculate it in the co-moving frame or whether you calculate it in the in the fixed frame. But this means that it doesn't change for any inertial system. So it's a Lorentz invariant. So if we define with F, this triple line here, it was meant to be a definition. Sorry. So defining, by definition, dn over dv, what is that? dn is the number of particles within this volume, elementary volume. So this is a density, particle density, number of particles per unit volume. And the number of particles, of course, is the same. You have 10 particles here, then in the volume possibly has changed shape when you move from one reference frame to the other, but the volume is the same, the number of particles is the same. There's the conservation of the number of particles. So it means that this ratio and this function doesn't change. So it's a Lorentz invariant. So this function, so the number of particles per unit volume in the phase space is Lorentz invariant. We call this distribution function. And this is something, so the density of particles in the phase space is something that you are probably already familiar with in other contexts. So far, you see that I assumed we were considering massive particles. Why? Well, I didn't stress it explicitly, but when I spoke in terms of co-moving frame, well, you cannot have a co-moving frame of photons, of course. There's no way you can have an inertial reference frame traveling at exactly the speed of light. So indeed, inevitably, this proof implicitly assumed massive particles. But, so in this sense, it's not immediately applicable to photons. But on the other side, there's no limitation to the energy and of the particle. So you can consider arbitrarily ultra-relativistic particles. But when the particle is moving at arbitrarily high Lorentz factor, it tends to behave like a photon, essentially. Also, if you think, for example, at the formula which expresses the energy as a function of the momentum, when the momentum is when PC is much larger than the MC squared, E is essentially PC, so the relation between energy momentum of a photon. So it is possible to kind of argue that this property, the invariance of the distribution function, also works in the case of photons. It can be demonstrated. I'm not going through it. But this is just, I like this because this argument is very elegant. So we proved it for massive particles, and in the regime of very ultra-relativistic particles, it still holds, so it can be arguably assumed that it will keep holding also for, instead of a number of particles, generic particles, number of photons, so massless particles, okay? Why is this important? This is, you say, you have to be patient for a little while. You will see why it is so useful to have proven the distribution function. So the density of particles in the phase space is an invariant, Lorentz invariant function. Let's introduce another quantity, which I call particle specific intensity, and I denote it with J. J is a function of energy. What is this? Well, this is the number of particles that are crossing a unit surface, a unit time, within an interval of energy. So all these particles having energy between E and E plus dE. And all these particles are moving within a given solid angle. So let's have a look at the drawing here, at this cartoon here on the left. So let's assume here, this is the coordinate space, so the three spatial axes. You have an element of volume here. You have a surface D, which we call dA. So you see all the particles are moving with this velocity, so perpendicularly to this surface, and they are going out of the surface within this element, solid angle element. So all these particles are moving along this d omega, okay? They are coming out of the source, coming out of the surface perpendicular to the source within this solid angle d omega. So there is a flux of particles coming out of the surface and directed along this solid angle element. So by definition, the particle specific intensity is just the number of particles per unit surface, so over the surface, coming out of the surface, so over the surface, over the time interval, so per unit time, over the solid angle, so per unit steradian, and over erg means you take just particles having an energy within a given interval of energy, so between E and E plus the E I said. So they have all the same energy, almost all the same direction within that solid angle. And we call it particle specific intensity, and that's the units of measure. Why this is interesting? Well, you can express, having introduced J, you can express the number of particles coming out of the surface going into the solid angle in two different ways. One way, which is the first equation here, just exploits the definition of J. Well, if J is the number, well, to have the number of particle dn, just multiply J by dA, the surface, multiply by the solid angle, given that it's defined also per unit solid angle. So if you look here at the units of measure, in order to have particles, you have to multiply by an area, centimeter square, so by dA. You have to get rid of the steradian, so you have to multiply by d omega. You have to get rid of the energy, erg, so dE, exactly the in energy interval. And finally, you get rid of the time of seconds, so by the time interval you consider. So to summarize, we consider the number of particles dn as the number of particles coming out of the surface perpendicular to the surface dA in a time interval dt, moving along a solid angle d omega, and all having energy between E and E plus dE. So the energy interval is dE. But you see, you can also express the very same quantity if you think of what we just talked about in the previous line as a function of the particle density distribution, F. So this will be F times what? Times the corresponding elementary volume in the phase space. Well, F is dN over dV, so dN is F dV. So F times dV, all this quantity following here, all these terms, is just dV. Let's see why. Well, dV in the phase space is just the product of a dV in the coordinate space times the corresponding elementary volume in the momentum space. So that's why we need the two spaces. That's why I drew both of them. So let's have a look at the coordinate space. The volume, what is the volume? Well, I'm considering all the particles crossing the surface within the time interval dt. And given that all the particles have almost the same velocity v, that means that the particle crossing this element will be just all the particles in this elementary volume whose section is dA, and whose depth is just v dt. Everything which lies inside will cross the surface dA in a time interval dt. Okay, so indeed the volume in the coordinate space that I'm looking for is indeed this three last term is dA v dt, and thus the volume, the part of the volume in the coordinate space. Let's have a look at the corresponding part in the momentum space. Well, they all of them have almost the same p. Why? Because they are moving well, because of what I said, they are almost having the same velocity, so the same p, but not exactly the same. There is some spread, which is over the solid angle. And the solid angle, if you think a little bit, is exactly the same. So d omega is exactly d omega p, where d omega p is the solid angle subtended in the momentum space. Because the direction of the momentum is exactly the direction of the velocity in the coordinate space. That's exactly the same object as directions, as spread of directions, as spread of possible directions is exactly the same. And so the volume, the elementary volume, with the particle having all p distributed over a dp interval, will be just this elementary volume shown here. So by definition, if you want, of solid angle, the area of this guy is just p squared d omega p. And the width of this guy is just dp. So this guy, p squared dp d omega p, is indeed the volume, this elementary volume here. But having said that the two delta d omega are the same, you equate the two things, you get rid of the common terms, and you see that you can express, you ended up with a formula expressing the particle specific intensity as a function of the distribution or a density dn, the guy that we call f, which is Lorentz invariant, times a number of factors, which are p squared v dp over de. Now, if you think carefully, all these three elements, p squared, v, and dpd, are somehow related, because they refer, just consider one particle of simplicity. P is not independent of v, and also how P changes as a function of energy is not independent. How to figure out this? Well, let's just start from the formula expressing the energy, the total energy as a function of the momentum. And just, if you calculate the differential of both terms, you see, you end up with an easy expression. EdE equals c squared PdP. So this allows you to get immediately dP over dE. So if you want, how momentum changes as a function of energy of a given particle. And what about VAP? Well, I remind you that in relativity, the momentum is gamma and V. So you can express V as a function of P and gamma. As a vector, yes, as a 3D vector. But again, if you multiply this term here, if you multiply by c squared, both, of course, the numerator and the denominator, you have that, okay, c squared, and below you have gamma mc squared. Gamma mc squared is the total energy of the particle, E. And this is a very, very handy formula. So if you remember that, that's very useful. Sometimes it's very useful to have a function, to be able to express the velocity of a particle just as a function of its momentum and energy. Just getting rid of the mass. Because when you change, for example, from a mass acid particle to a massless particle like a photon, this still holds. But if you have mass, then... So this is useful in general. But specifically here, so here we didn't take the entire vector, we just take the magnitude of the vector. Okay? So by replacing the last two terms, instead of V, I put c squared P over E. And instead of dP over dE, E over c squared P, you see that all these two terms among brackets cancel out. And you are left with a very simple formula, which expresses the newly introduced particle specific intensity as a function of F. So the distribution function and P squared. This is going to be useful for several reasons that we will see in a moment. But whenever you have something as a function of a Lorentz invariant quantity, and F is indeed a Lorentz invariant quantity, this can be very useful for the implications, for the consequences. The more Lorentz invariant quantities you deal with, the easier your life can be. I'm introducing a lot of quantities, so I'm not going too fast to allow you to understand things properly. So we already introduced the particle-specific intensity. Now let's introduce another quantity, which is the so-called specific intensity, which typically is referred to radiation. It is denoted with I, and given that we are thinking of photons, it's instead of as a function of energy, it's easier to think of as a function of frequency. That's why E as a function of nu. Look at the way it is defined, and look at the drawing, the figure on the left. So it's energy per unit time, per unit area, per unit frequency, per unit solid angle. So Erg per second, per square centimeter, per Hertz, per steradian. Let's have a look at the figure. So I have some radiation coming out of this elementary surface. And I want to express the amount of radiation coming out. Of course, the radiation will have its own direction, not only frequency, direction, everything. So I introduced this quantity, the specific intensity, which is defined as follows. It's the amount of energy coming out in a perpendicular direction to the surface. So it's energy per unit surface, per unit solid angle, per unit frequency, per steradian. So it means that if I want to express, okay, this comes later on. If I want to express the energy that is crossing the surface in a perpendicular direction to the surface itself, and which is radiated within the solid angle d omega, well, the total energy will be I times dA, the unit surface, time dt, time interval, time d nu, the frequency range, and time d omega. I'll get back when I will, presumably, surely next week, when we will be starting talking about radiative transfer, I will devote some more time on the definition of I. I will be our main subject, so we will be spending a lot of time. And this is just to get you acquainted with this. I'm just introducing you to this quantity. We will spend more time on it, on I. But this is relevant here because you can express now the same thing also as a function of the particle-specific intensity. If you know particle in the sense of number, not necessarily massive particles, okay? We are still having to do with photons. We are still dealing with photons. But particle is just the number. It counts the number. How many photons are crossing given surface per unit time, per unit solid angle, per unit energy. In this case, I is not the number of photons, is the energy. So between the two, the relation is rather simple. There's just a factor of energy. So I nu, d nu, is JEdE. So all the JEdE, what is that? Is the number of photons crossing per unit time, per unit area, per unit solid angle, and that's it, because I already multiplied by dE. But if I want the energy, I have to multiply by energy of the photons, which is E. So as a matter of fact, nu, d nu is just JEdE times E. Number times energy. And that gives me the energy. So the relation between, you see that there is a simple relation between I, the specific intensity, and the particle specific intensity. Particle in the sense of photons, number of photons, okay? So number of photons. This is just, apart from H, which is a Planck constant, there is just a factor of an extra nu. So you can express, for example, the result that we got in the previous slide. So the particle density we saw that is P square F, distribution function. So if you replace, instead of G, J, E, P, F, P square, F, and then you remember you want to everything expressed, we are talking about photons. So rather than momentum, you have both momentum and frequency, just put it in one unique variable. So you know that the momentum of a photon can be expressed as energy over c, but energy of a photon is h nu. So here the replacement I assumed is P equal h nu over c. Okay, just like that. So squared because it is squared. So you finally can collect all the, you can join the resulting dependence on nu, and you see that you gain a factor of nu cube. So in particular, I, except for the constant for the constants like the Planck one and the speed of light, let's focus on nu cube f. So I is proportional to nu cube f. This is interesting. Why? Because if, for example, you immediately appreciate by the definition of the specific intensity, that intensity is useful to describe how much radiation, for example, is coming out of the surface of a given object, which is emitting radiation. And if this object is moving with respect to us, observers, probably it's interesting to know how the function I changes when I move from one reference frame, which is, for example, the comoving frame of a source, to the observer frame. So one interesting question we would like to answer is how I changes when I move from the source comoving frame to the observer frame. Why? Well, for example, you know, I could describe a given process, and we will see many in the course of this, in the future lectures. So I is the result of some elementary process which produces radiation. But I know the properties of this in the comoving frame of the source, and the source is at rest. Now I have a source which is moving, in the most general case. So I wonder how I is affected. And this is the answer we are going to get. You see, if you look at the expression that I highlighted here, you already know that F is a Lorentz invariant. So when you move from the comoving source to the observer frame, F doesn't change. So it means that if you divide both sides of this equation by nu cube, on the left side, on the left-hand side of the equation, you have I over nu cube. On the other side, on the right-hand side, you have just F. So it means that I over nu cube is Lorentz invariant. You see? That's what I wrote here. If you work out the ratio I over nu cube, this is just proportional to F, but F is Lorentz invariant. So it means that the ratio between I and nu cube is Lorentz invariant. So it means that if I call I prime nu prime, what is that? Well, if I nu is the intensity, the specific intensity in the lab frame, I prime nu prime is the corresponding function as measured in the comoving frame of the source. And so what does this mean? Well, it means that the ratio between the two intensities scales as the ratio of the two corresponding frequencies. So if you put this guy here, I over I prime equals nu over nu prime cube. But you know the ratio between nu and nu prime. Prime is the comoving frame, okay? I used to call nu zero, the frequency of the photon in the comoving frame. Here, it's proper to call it, it's better to call it a nu prime, but that's the same quantity. So here I have that I over I prime scales as nu over nu prime cube, but nu over nu prime is, if you want by definition, the Doppler factor. Nu over nu prime is delta, what we call delta. So it means that I over I prime is delta cube. So we exploited the Lorentz invariance of the distribution function to prove how the intensity, the specific intensity, changes when moving from one frame to the other frame. In particular, its case with the Doppler factor cube. So let's explore exactly more in detail what this means. Who's this guy? Well, this guy is the specific intensity in the observer frame. So if I call mu prime the frequency of the photon in the co-moving frame, I know by definition of Doppler factor, if you want, that the observed frequency of the same photon will be delta nu prime. And if I look at that direction, I measure, according to all the definition I gave you of specific intensity, what I measure is I. The same quantity measured in the co-moving frame is I prime, which will be referring at a given theta prime, of course, because of the aberration of light. So to a given theta in the co-moving frame will correspond to a given theta prime. And so all the other independent variables. But the point here is that the delta cube. So if you move, for example, from the co-moving source here, I prime, to the observer frame, if the Doppler factor is larger than 1, so there is a boosting. So the effect is that if I am the source, I'm moving towards you, I emit a photon there. In my reference frame, you will see this photon pointing very close to my direction of motion, to you. The solid angle, you remember, d omega gets d omega prime, because this is my reference frame, becomes this way d omega prime over delta square, so much smaller. And the intensity that you measure in this is delta cube higher. This makes sense from a qualitative point of view because of what I said. The radiation is just put in this very narrow cone, and considering that also the photons have correspondingly larger frequency, so you have this totally resulting in gain of a factor of delta cube. So intensity increases as delta cube whenever delta, the Doppler factor, is larger than 1, of course. So this is something that we will use in many cases. There's also another much easier, much less elegant, but very practical, so intuitive. I just wanted to put it because it's intuitive. So when one, for the first time, just faces all these topics, it's useful also to have, as much as possible, an intuitive path to grasp the essential part of it. So just look at the definition of intensity. Intensity is energy per unit time interval, per area of the emitting surface, per Earth per steradian. So you want to understand what kind of relation between the quantity in the observer frame and the same quantity in the co-moving frame. So between these two guys. Well, you know that as soon as you know how all these individual terms change when you move from one system to the other one. So let's have a look. Let's look at the numerator. Well, you have nu, but you know that nu is just delta nu prime, Doppler factor. So the numerator here gains a factor of delta. If you want, this is just the definition of Doppler factor. Then I call dn prime the number of photons crossing that surface. We will see then, in the end, that it is the same. But let's have a look at the time interval, dt at the denominator. If you remember, when I showed you the intuitive approach, the intuitive demonstration, when I proved the formula of the Doppler factor in an intuitive, following an intuitive approach, we reason in terms of time intervals, arrival times, and I showed you at some point that indeed the relation between the two time intervals, so the time interval between the emission of the two photons in the co-moving frame and the arrival times of the observer, scale with 1 over delta. If frequency is frequency scale with a factor of delta, time interval cases in the reciprocal way, 1 over delta. So while nu, when moving from the prime to the unprimed system, frequencies gain a factor of delta, time intervals gain a factor of 1 over delta. If you want, just because of the dualism between frequencies and time interval, it's always the same thing. So dt is just dt prime over delta. But again, then we have the d omega, nu works like nu. So frequencies gain a factor of delta, so does d nu. And d omega, we already saw that d omega is just d omega prime over delta squared. The only two guys that I didn't comment, just that I put dn prime and dA prime, is just the number of particles and the surface element, the area of the elementary area of the surface element. These two guys are equals. Why? Well, the number is just the number. So the n prime is the n. dA doesn't change. I remind you that by definition of specific intensity, the surface has to be perpendicular to the direction of motion of the photons, by definition. And it is possible to show that this doesn't change. The easiest case in which this is obvious is if you consider that the source is moving exactly in a perpendicular direction to the surface. In that case, it's easier, it's immediate to say, because the surface belongs to the plane which is perpendicular to the line of motion, so it's completely unaffected by Lorentz transformation. That's easier case. This holds general. So I showed you in a very special case. It is possible to show, but it takes quite more calculation, so I'm not gonna spend my time because of that. But if you want, I can tell you which textbook shows you the full demonstration. So just to this, one can summarize this by saying that perpendicular areas are Lorentz invariant, perpendicular to the line of motion. Because what happens here, if you think of the photons are coming out perpendicularly of the elementary surface, you know that when you move from the source moving frame to the observer frame, because of aberration, the angle of the direction of motion of the photons changes from theta prime to theta, and as well the orientation of the elementary surface. The very same way, they keep being perpendicular to one another. So that's why the two areas are the same. And so you immediately see that if you work out all this gamma showing up and showing in the numerator, showing up in the numerator and the denominator, you see that in the end you are left with delta Q. This is exactly what we found. So this is more intuitive. It shows you where all the gammas come from, where all the deltas come from. Because there's a combination of definition per unit time, per unit frequency, per unit solid angle, and all combined together. This is the result. Beautiful. Having defined the intensity, it's also straightforward to define the so-called bolometric. Bolometric means that you, and this is general meaning, you are integrating something which depends on frequency or equivalently on wavelength, you integrate over the entire spectrum. Bolometric means that. So having said that this is the specific intensity, and in this sense, the word specific is always referring to frequency. So specific means per unit frequency. Here, the word specific drops. And instead of that, you have bolometric. It means you are integrated in the electromagnetic spectrum. So this is just, by definition, the bolometric intensity is just intensity. When bolometric is not said, the standard, the default is just bolometric, okay? So when nothing is said, if you want to mean specific intensity, you'd better say that, unless it is clear in the context you are dealing with. But otherwise, when nothing is said, it is meant to be bolometric. So it's just the integral of the specific intensity over d nu, as I said. So we can wonder the same. how this quantity, this bolometric intensity, changes when I move from one frame to the other. Easy. Now that you know how I changes, well, I knew we saw that it's just delta cube I prime nu prime, but nu prime, you can see, you can work out that integral as if you were making a variable change. So from nu prime is nu over delta. So you work out the very same integral. You remember that the Doppler factor doesn't depend on frequency, so you can take it out from the integral. Doesn't depend on frequency. And as I said, it's like a variable change of variable. So instead of nu, delta nu prime, and so you gain an extra factor of delta. An integral of I prime nu prime d nu prime is, of course, the bolometric intensity in the comoving frame, in the other frames. So again, the relation here is delta to the fourth. The bolometric. Bolometric because you integrated along the frequency, so you gained an extra factor of. Again, this is very useful. And it's worth stressing the units of measure of this quantity. Given that we integrated in frequency, you see, look at the units of measure of the specific intensity. You see, I integrated over frequency. So the only thing that disappeared is just per unit hertz. We have no more hertz. So it's, what is that? Is energy per unit time, per unit area, per unit steradian, per unit solid angle. And it's also nice to see the budget of all these, of where all these Doppler factors come from. So you have four of them. Two, so one comes from, look at the energy, units of measures. Earth, so you have energy or frequency. We are talking about photons. So when you move from one to the other, you gain a factor of delta. And then you have per unit time. So the time works the opposite way, but it's a denominator. So again, it contributes another factor of delta. And then in the end, you have a denominator solid angle, which contributes twice. So 1 plus 1 plus 4, as everyone knows, makes 4. And so that explains as well. Okay, I still have, well, we started a little bit later, so kind of 20 minutes, okay? So we'll be finished. Okay, let's change rather abruptly topics. But I think it is useful, unless you raise your hand, you say, and all of you say, no, this is really so obvious that I'm not gonna attend this. But I put this, the next slides, I wanted to put them based on my own experience as I was a student. I always, not always, for some time, I was a little bit annoyed by the fact, oh, I was taught with international system units, and now all of a sudden I have to use, which might sound like a little trouble, but then particularly when you work with electromagnetism equations, particularly with Maxwell equations, you see that they look apparently quite different. So it is annoying because some quantities have different dimensions. The same quantity in the international system has some units of measure and some dimensions, and the same quantity in the Gaussian system is different. So it took me a while to get used to that. So I thought it was useful for you because probably I think you might be in the same situation. But please, if you say, oh, this is really so obvious to me, just let me know so that I can gain time and we can. So let's have a summary. Let's make a summary of the fundamental quantities using magnetism. In particular, let's start from the international system. So you know that in addition to the three quantities, length, mass, and time, that you already know from mechanics, for which there was much more agreement historically. These quantities were introduced, I think, around 18th century, while the electromagnetism was born in a thanks to the simultaneous contribution of several people in the 19th century. So the story in that case is different. In any case, from the definition of the units of measure in the international system, one of the fundamental quantities is the current, the unit of measure adopted for the current, which is the ampere. And that's what I stressed here. And this holds for the international system. And the definition of ampere here. So if you take two wires, two infinitely long parallel wires, and you put them at a distance of 1 meter, so you have that the current flowing in these wires is 1 ampere when the force exchanged by the two wires is, in this case in vacuum, is 2 times 10 to minus 7 Newton per unit length, so per meter, of course. Historically, it was different, but then it was convened to reach up this definition. In general, it is possible to generalize the way one defines the units of measure. For example, I didn't mention, if you are already familiar with theoreticians usually adopt so-called natural units. They put Planck constant and the speed of light equal to 1. So essentially everything has units of measure in terms of as a function of mass. Length becomes mass. I mean, the point I'm making here is that the choice, this kind of choice, the choice for the units of measure is much more arbitrary than what one might think. Also the number of fundamental quantities. So we can generalize the approach what are the possible choices in the case of the electromagnetism by introducing some constants. In particular, we will see 4 constants, and then we will see the values assumed by these constants in the different unit systems, so that we can appreciate the different approach. So let's start from the basic law of electrostatic, which is the Coulomb's law. So you know the scaling, you know everything about that. I'm not going to comment except for the fact that you can put a constant, which we call K1, which automatically is a function of your choice. You know very well that in the international system, this guy is 1 over 4 pi epsilon 0. Why that? Because you already made the choice of the current unit. By the current unit, the definition of ampere, you automatically get the definition of Coulomb, the charge. So having said that, this K1 in the international system cannot be adimensional, because you already made an independent choice on the current and then on the charges. So here in the international system, Q and Q prime, the two charges are Coulomb. The force is a force, so Newton. So K1 cannot be adimensional, has consequently already some units of measure in the international system. If you consider another system, for example, you might think of defining the charge unit starting from this equation. So you say, okay, I consider a unit charge when when put at a 1 centimeter distance, I have 1 Newton, or no, 1 Newton, 1 dyne, for example, if you are. That defines K1. I mean, the value of K1 depends on what kind of choices you make. There are different possibilities, and that's indeed what happens when dealing with different systems. Of course, having defined K1 from the Coulomb's law, as a consequence, also the electric field unit is defined as a consequence, just F over Q. When you move on in the exploration of electromagnetism, and in particular to magnetostatic phenomena, which you don't have variable fields, of course you have phenomena, for example, Ampere's law. And what is related to Ampere's law? So, for example, the creation of magnetic field due to a current. So you can think of introducing another constant, which we call K2. And in this case, K2 is the constant which determines the force per unit length exchanged by the two wires, the very thing that I was mentioning in the definition of ampere for the international system. So you can generalize. Again, we are generalizing. Okay? We are going to a much higher level. And then we will see, depending on which system and so on which kind of choices you make, the different values. But you see, if you compare the two Coulomb's law and this one, you see that if you work out the ratio between the two side by side, you have a ratio between forces, so everything is known. So you immediately see that the ratio between the two constants that we introduced is not arbitrary. It has necessarily to be a velocity squared. There's no other way. Just work out the ratio from a dimensional analysis point of view. So your choice of K1 and K2 cannot be independent. They have dimensionally to be, their ratio has to be a velocity squared. But you can also measure experimentally, and you see that in the vacuum, this is just c squared, the speed of light squared. And this is already somehow introduces a constraint between K1 and K2. Okay, guy, you can choose K1 and K2, but you have to consider this constraint. You cannot choose both of them independently. That's the point I'm making. But still, there's one degree of freedom left. So depending on what choice you make, you end up with a different units system of units. Okay. When you consider it more specifically, so for example, I know, looking at this formula, I think of the Biot-Savart law. So again, when you want to measure, define the unit of measure of the so-called magnetic induction, then I usually call it magnetic field, but let's call it with the proper name, magnetic induction B. This is related to the K2, yes, because the greater K2 and the correspondingly proportional greater B, because essentially this is related to the previous equation. But again, if you want to have your own unit of measure for the magnetic induction, you have to allow an extra constant, which here I call alpha. Depending, maybe you have some reasons to have your own units of measure for B, so you have on one side to consider that this is proportional to K2, but at the same time you want something that allows you to have your own measure, to allow to make your own choice, alpha. And finally, you have to consider the mixture of the two fields. When, for example, with Faraday's law, you create an electric field just with a variable magnetic field, which is described as I said, by Faraday's law. Again, for the reason of convenience that you might have, you might want to have another constant, which again allows you some freedom in choosing the units of measure, which we call K3. But it is possible, again, when you mix the Maxwell equations, all the equations that you know, then in the end, you find out that they are not independent. In particular, you find out that K3 is the reciprocal of alpha. Why? Well, this is possible to see if you write down the Maxwell equations, including all these constants that we introduced. So, for example, you know very well the divergence law, Gauss-Green law, is the first law, which is telling you Coulomb's law. So K1 just shows up in that equation, and so on. So, for example, if you combine Ampere's law and Faraday's law, which are here the second and third one, in the case of vacuum, so no charges, no currents, nothing, and you work out in particular the curl of the first of Ampere's law. The curl in Italian is rotore. So nabla times is the curl, which I don't have, but the idea is the same. So the curl of, you work out the curl of both sides of Ampere's law. So you exploit this vector calculus identity. In particular, it's like the double vector product, very, very similar. So you see that you end up with the gradient of divergence of B. Divergence of B is just the absence of magnetic monopoles if you want. So you are left with this guy. On the other side, here j is 0, so you are left with the curl of the partial time derivative of the vector field. You can exchange both derivative, and exploiting the Faraday's law, you get this guy. So minus k3. Combining the two, you see that you have the wave equation. You know that, of course, in general. But what is interesting here, that you see you have this combination of the four constants that we introduced. We know that the value of that combined constant, what it has to be. Well, I already told you that k1 over k2 is 1 over c squared. And so inevitably, this proves that k3 is just 1 over alpha. So you introduced all these constants because some possibly potential reasons connected with the freedoms that you exploited to choose your own preferred units for measuring magnetic field, electric field, whatever. But then in the end, of course, they're not independent. So we have two constraints between K1, K2, and now between K3 and alpha. If you feel like you are just a mess, no, it's not a mess. Well, to some extent it is a little bit messy, but this is a way to come out of this mess and come out happy, possibly. You see, here I put 5 of the system of units. And for all of them, I put the 4 constants I just introduced. So you can immediately appreciate. And in addition to the constant, aside of the constant, I also put the dimensional analysis, you see. So when you see nothing, it means just one number. And in particular, let's focus on the 2 which I mostly care of, which are the Gaussian system and the international system. So you immediately see, so let's, for example, let's look at K1. You see in the Gaussian system, K1 is just 1. So there's completely different approach. While in the international system, it's something that you know very well. It's 1 over 4 pi epsilon 0, where epsilon 0 is the dielectric constant of the vacuum, having this value of 1 over as that value. That reflects the fact that, of course, the Coulomb, as you know, practically is a huge amount of charge. Well, the corresponding units of measure or charges in the Gaussian system is stat Coulomb, which is 3×10⁹ times smaller. But nevertheless, there are also other important differences that we'll comment in a moment. And also, you see the magnetic permeability, which shows up in the magnetic system, in the international system, has nothing like that in the Gaussian system. So this is the question which I immediately, when I was a student, I was wondering. And the reason is that they have different usages. In particular, the international system is typically preferred for large-scale phenomena, as I wrote here. And while the Gaussian system is something more akin to the needs of physics, of physicists, particularly when the particle physics, astrophysics, in many contexts in which elementary processes are more relevant. And so this is not my statement, but this is Jackson's statement. So it feels like, say, it may be, you might feel awkward having to deal with two systems, but scientists should be conversant with both in the very same manner that we are supposed to be fluently speaking English, just because of that, because language nowadays of science is English. There's nothing, no other reason. And here I just grabbed this table from Jackson, which is a kind of Bible of electromagnetism. I don't know if you know that. And in particular, this table is particularly useful because it summarizes a lot of things, in particular the values of the constants depending on the system. Here it's very general. D is the so-called electric displacement when you are considering electromagnetic fields within media, so with specific dielectric and diamagnetic properties. In this course, I will just consider it vacuum, at least vacuum with some charges and currents, but vacuum is, we don't consider medium, at least for the part of this course, which is relevant to this program. But in any case, this is a way to move from D to E, or H, which is properly the magnetic field, even if and B should be called magnetic induction, even if I will be calling all the time B as the magnetic induction, because they are equivalent. You see, in vacuum, essentially this constant in the this constant in the international system are the vacuum constant, epsilon 0 and mu 0. In the Gaussian system, it's just one. Anyway, you see the way you can express the Maxwell equations in one system and in one other. And the last column, the rightmost column, is the Lorentz force. This is also different because there is a factor of C difference. So it's worth pointing out. I also put this table because it's useful. It's a very handy table. It has a recipe. A recipe, you have an equation in one system. You want to express the very same equation in the other system. How to do that? Here, this table allows you to get the goal. How? Well, let's suppose you see two columns with all the quantities. Let's suppose you have an equation in the international system. You want to find the same in the Gaussian system. Let's suppose you have to look for all the quantities involved. Let's suppose there is a B, magnetic field. So having to go from international system to Gaussian, I look at B in the international system here, and I see that when I'm supposed to replace B, I'm supposed to replace B with B square root of blah blah. Remembering that 1 over square root of mu 0 epsilon 0 is equal C, that's the only thing you have to know. Then you can. Let's make a practical example. Let's suppose we start from Maxwell equations, probably in the form that is mostly familiar to you, international system. Let's set to ourselves this task. We want to derive Maxwell equations in the Gaussian system, which I'll be using several times. So let's apply the rules. Let's start from the first one. The first one, okay, I have electric field and charge density. So let's go back. Electric field here, you see, instead of electric field, I have to put electric field over square root of blah, blah, blah. And instead of charge density here, charge density times square root of. That's exactly what you do. Instead of E over what I find in that table, and instead of the charge density times square root of blah, blah. As I said, you just have to remember that. No, in this case, this is just straightforward. And that's indeed the first Maxwell equation in the Gaussian system. So you can keep on playing the same game. I'm not gonna go back and forth between these two slides. I invite you to carry out this game. If you end up being in control of this, it means that you can. And so, for example, the first thing I did, one of the first things I did when I was a student, I wanted desperately to know what the Biot-Savart law looks like in the Gaussian system. So that's like this. This is an exercise I advise you to carry out. So you see, I'm going fast because the time is running out, but you see, in this case, I found this, and then I remember that square root of mu 0, epsilon 0 is 1 over C. So just like that. And this is Ampere's law in Gaussian system. The third one, again, the same. This is Faraday's law. And well, this is trivial, of course. And this is the same. It's worth stressing a few things. So these are finally the two Maxwell equations in vacuum. I will not keep saying that. That's for granted, okay? In vacuum, now in the two systems, it would be nice if you could remember both of them. Particularly, I care mostly about the Gauss system. I'm not very keen on learning too many things by heart, but there are a few things that one has to. So it's not a big deal after all. I mean, there are other disciplines in which you have much more to learn by heart. So, so we will focus on that in particular. But I wanted to make sure that you can switch from one to the other easily, or at least that you know the recipe to do that. That's very important for me. I don't know how helpful this is for you. You will tell me at the end. A few points are worth to make. Unlike the international system, in the Gaussian system, the magnetic field and the electric field are homogeneous. They have the same unit of measure. You can see probably, well, even from Faraday's law, this is a derivative with respect to space, and this is derivative with respect to c dt, which is space. So you need to see that they're homogeneous quantity, same dimension. And we will see another advantage is that when you have a planar wave, so electric magnetic field oscillating, they have the same magnitude. The two vectors have the same, being homogeneous, they also have the same magnitude. They are equal in magnitude. Beautiful. And also to remember that the force, the Lorentz force, is a Q over C. Instead, in the international system, it's just QB times vector B. So remember that. This is, I'm not spending too much time on it. This is just a table for your own pleasure to see all the units of measure in the two systems, what is what, and how to convert one. I hope you are familiar with the equivalent with also the mechanical units. So for example, you have to know how many ergs 1 joule is, 10 to 7. You have to know that. As well as you have to know how 1 Newton, 10 to 5 dynes, and so on. This is the most important ones. At least the energy and by power is just ergs per second in the Gaussian system. And also the magnetic field units. You have the Tesla in the international system. In the Gaussian system, as you might guess, you have the Gauss. 1 Tesla, 10 to 4 Gauss. 10 to 4, magic number. That's all. As I usually do, this is the final list of references. I just put the references of the books, textbooks that I particularly used for the topics that you saw in this class. A general comment, I will number my lectures number 1, number 2, number 3, obviously, to some extent, but they are not, there's not a one-to-one correspondence with the lecture, with the classes. In my standard, in my convention, lecture is one topic, okay? So for example, we will go through lecture number 3, which will take us several classes. So just do not be confused. I'm not numbering the classes. Number of lectures is something different, okay? These are them in order. I just put in order. So the textbook that I mostly used is the BRAT, Astrophysical Processes, which has almost the same name as my course. Also Ghisellini. Ghisellini is a professor in Milan. He wrote this beautiful notes, very beautiful. He's one of the leading experts of the field. So, and also the Jackson. Well, Jackson is a Bible of electromagnetism. All these, the final slides that I put to discuss. If you want to go more in detail about this, all the aspects of the different units of system of units, Jackson is always a good reference. Barone is a very nice textbook for relativity, and Landau-Lifshitz is also classical. The last one I will comment on the next slide. So for today, that is it. Have you got any questions? Also remotely? Okay, so I just finished up in time just for lunch.